Hello. We are excited to present our recent work on accelerating RISC-V instruction set simulation, and the approach tier compilation is rarely used in low-level virtual machine like RISC-V instruction set architecture, but I think this topic is really interesting if you want to achieve higher speed for such purpose. Okay. So, RISC-V itself is a universal instruction set architecture. Besides the wider adoption in Silicon area, it is indeed used by many applications. Take GKVM, for example, is used by cryptography, and by means of RISC-V instruction set, we can have the strong ecosystem for the tooling support. And since RISC-V itself is widely used, so the performance of its instruction set architecture simulation is crucial, especially when we enter the requirement for multi-core simulations. So here, you already see there are similar model for many core or even the complex multi-core systems. So right now is a challenge that we do need a strong instruction set architecture simulator. Otherwise, it's unlikely to simulate and validate in a short time. So that's the reason we start the research. So we already expressed the demanding and the challenge for the RISC-V ecosystem. So at the moment, we just want to accelerate the execution. So our approach is to adapt, to modify and to change the idea behind high-level language virtual machines such as V8, Haspa, and so on. So we adapt idea of tier JIT compilation into the low-level virtual machine, in particular RISC-V instruction set simulation, and then we want to ensure that the simulator itself is always consuming less system resources. Therefore, we can make the simulation more scalable when we want to achieve the multi-core simulation. I think the system consumption is really key aspect during the simulation. Meanwhile, we want to make sure the code base is small and readable, which suitable for the research purpose. I think most of you already familiar with multi-tier JIT compilation. So the idea behind multi-tier just-in-time compilation is we can convert the complex operation into the much smaller ones. So for the first tier, it usually just nail down the scope for instruction dispatch, up to operation, or even for the type systems. And for the second tier, it is usually deploy several optimization techniques. So there are some essential optimization techniques applied in the second tier JIT compiler. And for the last tier JIT compiler, we can apply several aggressive optimization techniques. But the question is, if this approach suitable for low-level virtual machines such as RISC-V instruction set architecture simulator. Before answering the question, we just review the existing work. So here you can see hotspot virtual machine, which is dedicated to Java, and we have the V8, which is dedicated to JavaScript, and PyPy, which is built on top of Python. So these virtual machines are very excellent, and we do want to learn the idea behind this virtual machine. But however, these virtual machines are designed for the high-level virtual machine, meaning that it's totally different scenario when we want to focus on RISC-V virtual machine. In the other hand, if we go back to the open source implementation for RISC-V instruction set architecture, we can see there are already some notable implementation. So here, Spike. Spike is a famous virtual machine maintained by a RISC-V Foundation. So itself is an interpreter, and it was designed for the correctness. So meaning that many developer and many company can contribute RISC-V and its extension based on the Spike. And the Python 4 is very interesting implementation. It is built on top of Python, which is part of PyPy toolchain. So the Python 4 itself can apply several interesting optimization strategies, and then it's possible to achieve a bit higher performance. However, it consumes too much memory, making it almost impossible to be suitable for multi-core systems simulations. And RV8 was an excellent implementation. However, it is now unmaintained, meaning that it's not suitable at the moment. Humil is the most famous implementation as for the system and the instruction set architecture simulator. It's very, very excellent in the performance. However, it lack of the aggressive optimization. Despite the efficiency, Spike itself as an interpreter still making sense to the ecosystem of Silicon and the software developer because it's quite small and efficient, meaning that we do not encounter the potential attack from the JIT implementations. So advanced JIT virtual machines such as V8, there are many security attack surface, and Spike itself is good for reference implementations. QMIL is notable for its TCG, which means tiny code gen. TCG itself is portable, meaning that we can use TCG to generate many architecture, including ARM, MIPS, and some pseudo instructions. However, its limitation, I mean, the limitation of the QMU is it only implements the batch optimization strategy, and it's unlikely for QMU to change its IR because of the comparability, since it is widely adopted by many companies. So the community member want to make sure QMU can be improved, but at the same time, its compatibility must be ensured. So our idea is we want to accelerate the execution of RISC-V instruction set simulation. Meanwhile, we took the approach we called interpreter-first strategy, meaning that we focus on the interpreter at the first time, and then we want to make sure interpreter can work as expected, and then we extend its functionality, such as being a profiler for the whole virtual machine. Also, we want to make the aggressive optimization available by means of offloading the optimization to existing compiler framework such as LLVM. And the last tier JIT compilation should be pluggable, meaning that it's possible to replace LLVM with other implementation. In fact, we are doing such tasks. So we try to integrate systems simulation to validate our work. At the moment, our work is capable of booting and running Linux applications. So our work is no longer just a proof concept. I think it is workable, and it is beneficial to the ecosystem as far as I know. There are several key components. The first thing is an interpreter. In fact, it is used not only for the instruction set simulation, but also it is used for the runtime profiler. So, meaning that it has to correct the runtime information and to identify the performance hotspots. Then it will trigger the JIT compilation on demand. And we designed two-tier just-in-time compilation. So for the first tier compiler, as long as T1C is used for to generate codes very fast. So only batch optimization are present in T1C. And for the tier 2 JIT compiler, it's possible to enable aggressive optimization. At the moment, we use LLVM, and later we will try other advanced optimization framework as well. So right now, I will show you the architecture here. Everything starts batch block. So we just design our own IR, which is quite straightforward and simple. So we just convert the RISC-V instruction into the counterparts defined in our IR, and then we try to figure out the performance bottleneck by means of enabling the runtime profiler. So there are two kinds of conditions. One condition is it is not performance hotspot. So if it is not performance hotspot, I mean for the most case, so we just use the pure interpreter. And then if we are able to determine the performance hotspot, well, we split the two conditions. One is the strong hotspot, meaning that is feasible to invoke LLVM to perform aggressive optimization. And for the remaining case, we call it the potential hotspot. So for this case, it is involved more work. So right now, for the potential hotspot, we try to invoke the tier 1 JIT compiler and generate machine code as fast as we could. And later, we can correct the runtime information. Then it could be the feedback for the further optimizations. Let's focus on the interpreter at the first glance. So, as I mentioned earlier, we designed our IR, which is linear. I mean, this is quite straightforward. Itself is built on top linked list. So, from the diagram, you can see there are many nodes, which becomes the chain of IR nodes. And we apply the technique so-called block chaining, which was introduced by QMU. So QMU used block chaining to reduce the overhead of instruction dispatch. And the technique can help branch prediction, and then it's possible to improve the cache locality since we don't have to pay attention to frequent instruction dispatching. So this technique is quite useful, and we just modify modify our interpreter to make use of the block chaining technique. And we try to analyze the existing RISC-V code, and we found there is an interesting opportunity to optimize the code. So right now we can apply the idea we call it a micro operation fusion, meaning that we can combine several RISC-V instructions which are executed frequently. So we can combine several RISC-V instructions into a single instruction. So like this, we have found several patterns. So we will just provide the smaller counterparts, meaning that we can eliminate the instruction dispatch overhead. And from the preliminary benchmarking, the technique is quite useful. So you can see take Drystone, for example. Its performance could be improved by applying a single idea, I mean, macro operation fusion. And we apply the common optimization strategies such as constant propagation and constant folding. So apply such optimization strategy, the interpreter could be a bit faster since we can, again, we can eliminate the overhead of the instruction dispatch and get the deterministic execution as well. And as I mentioned earlier, we concentrate on the system resources usage. So it's necessary to ensure our implementation could be function not only for the faster execution, but also to be resources efficient. So we try to integrate some notable memory allocation strategy. So right now, we can use LFU, which is quite straightforward and is quite useful. So we can make the memory consumption as low as possible. Sorry. So we will just pick out some micro benchmark to validate the efficiency. And you can see comparing to the baseline, the strategy is quite positive and quite useful from benchmark perspective. And compared to the spike, our implementation of the interpreter could be much faster. And the next stage is we want to introduce the aggressive strategy to isolate the JIT compilation. Yeah. So, please.
Maybe 5 more minutes.
Okay.
Okay, here is our design of our JIT compiler. First, we want this compiler translates the IR into the host binary to improve the efficiency. But we want to only compile the hotspot because the overhead of the JIT compilation is heavy. And the benefit from the JIT compilation might be cancelled by this overhead. Our first JIT compiler is the simple one and only does some do some optimization, but important one. And if the other one hotspot is detected, we invoke the tier 2 compiler to compile the hotspot. But how do we categorize the hotspot to appropriate JIT compilation? We use the runtime profiler. The runtime profiler divides the hotspot into 2 types, the potential one and the strong one. The potential one is the block which execution count exceeds the threshold we set, or is a part of a loop. The strong one is the potential hotspot. The execution count of the potential hotspot exceeds the threshold again, and it becomes a strong hotspot. This is the workflow of our runtime profiler. If the hotspot is detected, it go to the middle path and generate the target machine code. And the target machine code is invoked. The execution count of the target machine code is exceed to the threshold, and it becomes the strong one and go to the button pad. And I have mentioned in this page, the second one is the detection of the part of the loop. And how do we detect the loop? We have two methods to we have evaluated 2 methods to detect this loop. The first one is based on the backward jump. If the backward jump detect, we directly offload the execution to the JIT compiler, and this may sometimes break down the internet loop. So we decide not to use this method. And the second one is trace the interpreter execution path. We initialize the set and insert the basic block into the set. If we found the basic block is already in the set, a loop we found. So the second one is better for the loop detection. And the right side is the proposed loop detection. And left side is the first method, and it breaks down the two interloop to the small piece, and we don't want this appearance. Okay. Skip. The implementation of our Tier 1 compiler. First, we prepare a code cache. We need to create the executable memory page by the mmap system call, and provide a function product and an app log to reverse the host register value. And the LFU cache replacement is used in our implementation if the code cache is full. The execution flow is shown below. First, we enter the product and jump into the translated block. If there is any Chen block, it keeps going to the Chen block, and finally it comes back to the app log and return the control flow to the next to the interpreter of the next block of the JIT compilation. Okay, we introduce another a technique to do the branch prediction to solve the interval jump problem in a dynamic binary translation. In many dynamic binary translation, the interval jump we cannot the target address of the interval jump is determined by the register value in the runtime. So we cannot do the block training before the program is actually executed. So to address this problem, we record the history of the target address when the interpreter is executed, and then once the JIT compiler is executed, is invoked. The most frequent jump target is to we generate a branch instruction for the most frequently jump target.
So running a little
conclusion.
Okay.
Okay. The tier 2 compiler is we use the LVM framework.
So I just to summarize the proposed numbers for you. So right now, not this one. So right now, if you compare Cumul and our work, it's possible to assure the feasibility of JIT compilation. However, the number was not so evident as we expect earlier. So it is because we still have to nail down some potential proposed improvement, such as more indirect jump improvements, as we mentioned earlier. And still, if you compare the work with the native execution, the result was promising. And however, some terms like 14-point emulation and string sort, they were not as good as we expect. So we need more we need more work there. So I think it's an interesting strategy to introduce multi-tier JIT compilation into the system-level simulation, and I think it's doable. However, we figure out some potential improvement strategy, and right now we want to show you the results. And at the moment, it's capable of booting Linux and running complex user program at the moment. Thank you.
Please, let's have some questions. Please, questions. Okay, please.
Thanks for the great talk. So if I understand right, you were using like a trace JIT-like upload where you trigger the compilation depending on the performance of the basic code ideas, and I was just wondering whether you consider using more like a method-based JIT upload where you trigger the compilation depending on the performance of the. Can you hear me? Okay.
I think you can just speak. It's not such a big room.
Yeah, this is recorded. Sorry. Should I
Yeah.
repeat the question? So if I understand right, if I understand right, I think you're using the trace like JIT where you trigger the compilation depending on the hotness of the basic probe. I was just wondering whether you consider using the more like a method-based JIT.
Okay, so our major idea is we want to speed up the execution of RISC-V instruction set simulation, in particular for the multi-core system, meaning that it's impossible to isolate every processor core. We must highlight the performance hotspot, and then we want to offload the aggressive optimization. So our consideration is can we just nail down the system resources utilization at the first moment, and we apply some idea to profiling the system not only for the virtual machine aspects, meaning that we do not only the loop detection, but also how can we balance the computing in the multi-core system simulation. So I think there is a room for identify the potential hotspot and try to make it practical for such topic. Thank you.
So, especially with LLVM, how do you handle traps and faults like invalid memory accesses.
Okay. The question is about the fault and MNU handling, right?
Sorry?
Your question is about the trap
Yes.
and the fault handling.
Yes.
Okay. For system simulation, that's necessary. And in the paper of VMIL, we lack of such discussion. But it is quite challenging that you have to convert the memory operation since the memory model is different, and including the barrier, memory order, TSC, and so on. So we have to predict the behavior of the running system. So we implement yet another system profiler for Linux system by insert the Linux kernel. So it's some kind like a perf variant to correct this runtime information. And if we can utilize the runtime information, we can then to predict the memory operation and try to replace the operation with the shortcut one. Okay.
Thank you.